Hello, this is me, Hugo, and I'll be doing the first part of three parts of the 2020 Level 3 Chemistry Aqueous Systems paper. So let's get started on question one. Okay, we've got some buffer questions. So, aqueous solution, mixture of ammonium chloride and ammonia, act as a buffer solution. You got Ka and pKa, give the pH range for which the solution will act as a buffer. So the general rule of thumb of the pH range of the function of a buffer is the pKa plus minus 1. So in this case, the range would be, let's write pH range is equal to, well, 9.24 minus 1 is 8.24, plus 1, that is 10.24. Right, that's your answer. Explain why the addition of a small volume of nitric acid to the buffer solution will not result in a significant change in pH. Right, so in these sorts of questions, what I like to do is just define what a buffer solution is first and what it does. So let's just write down the function of a buffer. So the function of a buffer is to resist large changes in pH upon addition of small amounts of strong acids or base. Right? So now in this question, what we're looking at is actually when we're adding nitric acid. So let's talk about what happens when nitric acid is added. So when nitric acid is added, it will react with the basic component of the buffer. And in these questions, it's really useful to link it to the context. So the context in this, we actually have a ammonia buffer. So our basic component is just ammonia. So let's just put in brackets NH3 in a neutralization reaction. Yeah, in a neutralization reaction. To form water and the conjugate acid of the base. So what this looks like in the equation is our basic component, which is ammonia, and that reacts with acid, which we represent as hydronium ions. Now we don't necessarily want to write nitric acid because this is much easier to show a neutralization reaction because it's just pure acid particles, and nitric acid is a strong acid, and so it will fully dissociate into hydronium ions. So this will react, and this will give us water, and this will act as a base, and so it'll be a proton acceptor, so you get NH4 plus, right? So what this does is the strong, we form a weaker acid, NH4 plus, compared to nitric acid, therefore resisting a change in pH. Cool. Next question, it's a calculation. So let's see. Calculate the mass of ammonium chloride. Must be added to 200 mils of 0.05 moliliters of that to give a buffer solution with a pH of 8.75. And we're given the molar mass. Okay, so here we want to start off by using the Henderson equation. So that is pH equals pKa plus log of concentration of base divided by concentration of acid, right? And here we are given the concentration of the base component, but we don't have the concentration of the acid, which is what we're working out here in the ammonium chloride. So, but we know the pH, 8.75, and we know the pKa, which is up here, 9.24. So let's put our information as of 8.25, which is pH, equals 9.24 pKa, plus log of concentration of our base, which is, 0.05, divided by the concentration of the acid, which is NH4+. Now let's just solve the equation to find the concentration of ammonium ions. So we get log of 0.05 divided by concentration of ammonium, and that is equal to, well, 8.25 minus 9.24, negative 0.49. Now you get rid of the log, 0.05 divided by NH4 plus equals 10 to the negative 0.49, which is also equal to 0.324. Now we can rearrange to solve for NH4 plus. NH4 plus equals 0.155 moles per liter. That's cool. Okay, and this, now we have the volume of 200 mils, so you can say the volume is 0.2 liters. Therefore, the number of moles of NH4 plus is equal to 0.155 times 0.2, which is equal to 0.0309 moles. Okay, now in ammonium chloride looks like this, right? So there's a 1-to-1 ratio. So there's one ammonium, and so therefore, however many moles of ammonium we have, it's going to also equal the number of moles of ammonium chloride, right? And now, using our formula of N equals M over M, we're trying to find the mass of it. So mass is equal to N times molar mass, which is, our molar mass is 53.5. So 53.5 times 0.0309, and you should get a mass of 1.65 grams. And that is your answer. Cool. Moving on. Okay, so explain whether the buffer in part I be more effective at neutralizing a strong acid or a strong base. Right. So the thing is here is, if pH is it's greater than pKa, then there is more base, so more base. And if pH is less than pKa, then we have more acid, right? Because if pH equals pKa, then there's equal amounts of acid and base as the Henderson equation. So if we have pH equals pKa plus log of concentration of base divided by acid, if we have equal amounts, then we'd have pKa plus 0, which is just pKa, right? So these are what you need to know when discussing the effectiveness of buffers. So let's look back at our pKa, which is 9.24, and our pH is 8.75. So in this case, the pH of the buffer is 8.75, whereas pKa is 9.24. Since pH is less than pKa, there is a greater concentration of the acid, in this case it's NH4 plus, than the base, which is NH3. Therefore, with more acid particles present, the buffer is more effective at resisting changes in pH upon addition of a strong base. And this makes sense because if we have more acid than base, then we have more acids to work with, and acids react with base, so it's going to be more effective against strong bases. So that's what you would write for that. Cool. Solutions of equal concentration were prepared for each of the following. Rank the order in decreasing pH. Right. So this is basic. So that's obviously going to be the highest of the three because this is a strong acid and this is a weak acid salt. So CH3 NH2 is up here, and then this is a weak acid salt, so it's going to be weaker than a strong acid, so let's put that here, and then let's put hydrogen bromide here. Now we need to justify the order. Okay, so let's see. We'll justify the first one, so that is CH3 NH2 is a weak base. Therefore, upon dissociation, OH minus ions are produced. Therefore, the concentration of hydronium ions decrease as Kw equals hydronium ions times hydroxide ions. Right, so that is relating to the concentration of hydronium ions. So the concentration of hydronium ions decrease, hence pH is greater than 7. Right, and let's just write an equation for that. So CH3 NH2 plus water is in equilibrium. NH3 plus OH minus. Cool. On to the next. NH4Cl is a weak acid salt that dissociates to produce the ammonium weak acid. Ammonium will partially dissociate to form some / little amounts of hydronium ions, right? And let's write an equation for that. So NH4 plus aqueous plus water, that, and then plus hydronium ions, right? So because it's a weak acid, it only partially dissociates, so it increases the hydronium concentration, but just by a little bit. But it's still a weak acid, so it is acidic compared to the basic methanamine. Okay, now working with hydrogen bromide. So hydrogen bromide is a strong acid, therefore will fully dissociate to form a high concentration of hydronium ions. Right, so let's show that in the equation. So hydrogen bromide, aqueous plus water. It's a strong, so we only do a one direction arrow. We get bromide and hydronium ions. Yep, that's good. Yeah, on to the next one. If that has a pH of 4.7, calculate its concentration. Okay, so we have pH. First of all, let's write out the equation. So what we're interested is in the ammonium aspect of ammonium chloride. So ammonium will react with water and will form these products, right? And so we can write the Ka is equal to NH3 times H3O plus divided by the concentration of NH4 plus, right? And I'm sure we're given it in the question. Yep. So Ka of ammonium is 5.75 times 10 to the negative 10. So this is equal to 5.75 times 10 to the negative 10, right? Now notice here that the concentration of ammonia is actually equal to the concentration of hydronium ions because of the equation given above. The molar ratio is 1 to 1. So we can say here that concentration of ammonia is equal to the concentration of hydronium ions, right? So that's good. So we can rewrite the expression as concentration of hydronium ions squared over the concentration of ammonium equals 5.75 times 10 to the negative 10. And the question we're given that pH equals 4.7. So on the side, we can write here that concentration of hydronium ions equals 10 to the negative 4.7, which is equal to, let's put that in the calculator, 10 to the power of negative 4.7. That's about 2.00 times 10 to the negative 5 moles per liter, right? So then let's put that in our equation. So 2.00 times 10 to the negative 5 squared divided by the concentration of ammonium equals to 5.75 times 10 to the negative 10. Rearrange to solve for ammonium, concentration of ammonium, and you should get 0.692 moles per liter. Cool. And again, since it's a 1-to-1 ratio with ammonium and ammonium chloride, we can say that since it's 1-to-1 ratio, the concentration of ammonium will also be the same concentration of ammonium chloride. So that's your final answer. Cool. And that is the end of question 1.